So this problem relates to how sequences combine together with the ordering of the real numbers, right? So we have a theorem, theorem 2.18, which is in the text, that says if I have two sequences, the SNs and the TNs, and if all the SNs are less than or equal to the TNs, right, then if both of them are convergent, then the limit of the SNs is less than or equal to the limit of the TNs. So if it's not possible for the S's to be bigger than the T's, then it's not possible for the limit of the S's to be bigger than the limit of the T's. And so the point of this problem is to see what would happen if this permissive inequality were replaced with strict inequality. So if Sn is less than Tn, but the limit of the SNs is not in fact less than the limit of the TNs. So does somebody want to give just one example of a pair of sequences that they used to illustrate that this can happen? Alyssa?
I got 1 over n and then negative 1 over n.
Okay. So 1 over n. So Sn was 1 over n?
Yep.
And Tn was minus 1 over n? Did I have that right? There we go. That makes sense. Right, so sure enough, each of these is convergent. What do the TNs converge to? 0. And the SNs converge to 0. Is it true that the SNs are always less than the TNs? Yeah, it's true. All the SNs are negative. All the TNs are positive, right? So that works. But it's not true that the limit of the SNs is not less than the limit of the TNs. But the limit of the SNs is 0, and that's not less than the limit of the TNs. Right, so clearly there is more than meets the eye to this order argument, and there has to be something going on in the proof of theorem 2.18 that makes it necessary for us to use the permissive inequality rather than the strict inequality. So let's take a look in that proof and see if we can spot where it is that we can't replace the less than or equal to's with less thans. One way we could try to approach this is just by trying to replace some of these less thans, or sorry, some of these less than or equal to's with less thans in the proof. Walk back through this proof step by step. So we start with two convergent sequences, Sn and Tn. And capital S is the limit of the SNs, capital T is the limit of the TNs. So let's suppose that the green sequence up here are my TNs, and the, what are these, purple sequence are my SNs. So here are my TNs, and then down here are my SNs. And then each of those sequences are convergent, so that means that there is some value, they call them T and S in the actual proofs. So this would be capital S, and then this would be capital T, to which they converge. Right? Okay, right. Let's talk about the epsilon over 2 for a minute. So let's actually read this proof kind of from the bottom up, because again, this is a classic example of a proof where the proof writer has done some work on a piece of scratch paper somewhere and then pulled out something that doesn't seem to make a lot of sense. Right? They pull out these epsilon over 2's out of nowhere. And the reason that those epsilons over 2 come out of nowhere is that the proof writer has kind of said, well, if I want to show that the limit of the SNs is less than or equal to the limit of the TNs, what they've done is taken this inequality and rearranged it by subtracting one side from the other. And so what they endeavor to do, they subtract the limit of the SNs from both sides, and they come up with this: 0 is less than or equal to the limit of the TNs minus the SNs, as n goes to infinity. And so this is now the statement, the equivalent statement that they're going to try to show. Right? So they want to show that if I subtract these two sequences, that the limit is greater than or equal to 0. The problem is each one of these sequences is converging to a different, perhaps, limit, right? Capital T and capital S. And they might be converging to those limits at different rates. And so what they want to do is they want to come up with a way to quantify this limit that lets us relate, well, we want to use a definition of convergence here. Right, so this is equal to t minus s. And we know this is equal to t minus s just by the limit property theorems. Limit properties. But the tricky bit is that we don't have a relationship between any epsilon that we might pick and the n which might work for one of these sequences might be different than the n that works for the other. So what the comparison that we want is, so let's look at this line down here. We know that term by term, the t's are all greater than or equal to the s's, right? And so what we can say just right up front is that tn minus sn is greater than or equal to 0. So this is a sequence whose terms are all non-negative. Then they use this add and subtract trick here in the middle that lets us take the difference between tn and sn, the nth term of the t sequence and the nth term of the n sequence, and relate each of them to their own limit. Right? So we are going to have some control on how tn relates to t, because we know tn converges to t, and we're going to have some control on how sn relates to s, because sn converges to s. So thematically, we have control over both of these two pieces by the assumption that those sequences converge. We have some control here, and we have some control here. But because we have that control in two different places, if we want to make an argument that, that this sum can be controlled by a quantity epsilon, then we're just going to split up that epsilon so that each one of these two pieces which we can control gets half as much as epsilon. So that's where these epsilon over 2's come from. The argument isn't that different if we just replace them with epsilon itself. Like if I just made this epsilon, and I made this epsilon, then in the argument down here, this becomes epsilon, and so then the statement here on the next line becomes minus 2 epsilon, which doesn't actually change our argument much at all, because let's look at the last part of what's going on here. The last part says, I'm going to go back to the epsilon over 2's for a minute. The last part says, after our add and subtract trick is over, we've shown that for any epsilon, so our epsilon was chosen for us here at the beginning. Right, suppose epsilon is greater than 0. For any value of epsilon, it's true that t minus s is greater than minus epsilon. So if we look on a number line, so 0 is right here. Any epsilon that I pick is going to be greater than 0. But if epsilon is greater than 0, where is minus epsilon? Less than 0. Okay. No matter what epsilon I pick, minus epsilon is going to be less than 0. And this algebra that's done here in this line shows me that t minus s is definitely greater than minus epsilon. Right? No matter what epsilon I pick, t minus s is going to be above it. So why does that prove that t minus s is equal to, well, it doesn't prove that t minus s is equal to 0. But why is it not possible for t minus s to be negative? Let's run this by contradiction. If t minus s were negative, then why would this be a problematic argument? Well, yeah, but that's a circular argument. What I'd like to know is why is this statement, the statement that t minus s is greater than minus epsilon for any positive epsilon, why is that a problem if t minus s is negative?
Because then you could find an epsilon, and epsilon to the negative epsilon would be greater.
Yeah, exactly, right. If t minus s were in fact negative, then I could find an epsilon. So what would be an example of such an epsilon? How about just t minus s over 2? As an example, right? If epsilon were t minus s over 2, then minus epsilon would no longer be less than t minus s. Right? if t minus s were negative, then there exists an epsilon greater than 0 with t minus s not greater than minus epsilon, right? And so the statement down here at the bottom, in fact, shows that t minus s must be greater than or equal to 0, because it's not possible under those circumstances for t minus s to be negative. But what if, by chance, I think that what Alyssa was seeing as a bug in the argument is actually the feature that we need in this argument. The feature that if we replace the less than with less, sorry, if we replace less than or equal to with less than, nothing else in this argument at the end here changes. But what was the conclusion of this argument? If minus epsilon is less than t minus s, then that means that t minus s is positive or 0, right? Is greater than or equal to 0. And so no matter what, we still come out with the same conclusion that, not the SNs, but the limits of the SNs and the TNs are not guaranteed to be less than, but in fact less than or equal to. Let's imagine a world in which that were the statement we were trying to prove, that we assume Sn is less than Tn, and we try to prove that the limit of the Sns is less than the limit of the Tns using this same proof. Everything in this proof now, as it's written, is flawless, right? The assumption that S and T are convergent leads us to the ability to have some control over the difference between Sn and S and the difference between Tn and T, just by definition. We can use epsilon over 2 or epsilon, it doesn't really matter. And then as long as the n that we choose is bigger than or equal to both of the n's that we got from these definitions, then both of these inequalities will be true for n greater than or equal to that capital N. And then in that case, 0 is less than Tn minus Sn because of this. And that's equal to, using the add and subtract trick, this, and then using the definition of convergence, that. And then when I add these together, I still get this inequality, right? T minus s has to be greater than minus epsilon. But that statement is true for any positive epsilon that we choose, which tells me that t minus s is greater than every negative number. Maybe that's another way to say what's actually conveyed in this part of the argument down here. So just to highlight it again, minus epsilon is less than t minus s for any positive number epsilon. Another way to say that is that t minus s is greater than every negative number. But what does it mean to be greater than every negative number? Or 0, right. This implies that t minus s is either 0 or positive. But the point is, we weren't able to rule out the case where t minus s might be 0. Right? So this line of argument that we have here is not sufficient for us to get the strict inequality that we're looking for. Right? Because our proof leaves open the possibility that we could have, still could have, equals here. So that's the flaw. I mean, the way that this proof is set up is not a strong enough argument for us to get a strict inequality out of the proof, even if we put a strict inequality in.